In our last lecture, I introduced the concepts of parametric and nonparametric statistical tests and briefly mentioned that parametric tests include an assumption of normal distribution, while nonparametric tests do not. Our final pause before discussing specific tests of inferential statistical analysis is to clarify the distinction between parametric and nonparametric tests. Following this lecture, students should be able to compare and contrast parametric and nonparametric statistical tests, explain the assumptions of parametric tests, explain the assumptions of nonparametric tests, and discuss when and why to use a nonparametric test instead of a parametric test. Parametric and nonparametric tests are two broad classifications for tests of inferential statistical analysis. Parametric tests require data to follow specific probability distributions, like the normal distribution, and make inferences about population parameters, such as the mean. Parametric tests use the mean of the data collected in their computations, which is a large component as to why a normal distribution is a required component for using a parametric test of statistical analysis. Remember from our earlier lectures that if the data is not normally distributed, the mean can be pulled in one direction or the other. Nonparametric tests, in contrast, make fewer or no assumptions about data distribution and are used when parametric assumptions are not met. Nonparametric tests rely on rankings or medians instead of the means when comparing and analyzing data. Parametric tests, therefore, are generally more powerful than nonparametric tests if their assumptions hold, but nonparametric tests offer greater flexibility and are able to handle skewed and smaller data sets. I want to be in that each specific parametric test is going to have its own specific set of assumptions that must be met in order for the test to be used. However, there are some general assumptions that are common across many parametric tests, and these assumptions should sound familiar to you, as I did briefly mention them during our lecture on hypothesis testing. Recall that step 3 of hypothesis testing is to check the assumptions of your chosen test. I want to discuss these assumptions in a bit more detail now, as a solid understanding of the assumptions is important for making decisions on what test to use when you are the investigator and when critiquing literature, and considering if the test used by the investigators in statistical analysis was the appropriate test, and if the assumptions of that test appear to have been met or not. Because remember, if the assumptions are not met, then this jeopardizes both the internal and external validity. I am discussing the assumptions in detail now, and when I go over the individual tests, if it is one of the assumptions I have already explained to you in this lecture, I am not going to review the assumption in detail. You have all of the assumptions in this one location explained for review. I am hoping that this will help with brevity and clarity of the future upcoming lectures. The first assumption of parametric tests is the assumption that the data are normally distributed. You may be wondering which variable or which factor of the data should be normally distributed. This is an excellent question, and the answer will depend on which parametric test you are using. For example, the t-test, the independent t-test, is looking at the dependent variables being normally distributed. Other tests look at different variables, and we will discuss those in the upcoming lectures. The second question you may be asking yourself is, how do we confirm that the data are normally distributed? There are a few options that you can use to go about confirming normal distribution. First, you can visually check for normality using either a histogram or a PP plot. We have discussed histograms previously, and with the histogram, remember you are looking for a bell curve to confirm normality. This is the first time we have discussed PP plots. A PP plot is a cumulative probability distribution of a variable against the cumulative probability of normal distribution. And you may be thinking, what does that mean? Simply put, that means when you look at a PP plot, you want to see the majority of the data values fall either on or close to the diagonal line of the standard normal distribution. If the data values do not closely follow this line, they are non-normal. To obtain a PP plot of your data, you would use the statistical software that you plugged your data into and run a PP plot. You should see the normal distribution line running from the bottom left of the screen to the top right, and you look at how closely your data values follow this line. Another method to check for normality is to look at the measures of skewness and kurtosis. If the data are normally distributed, both the skewness and kurtosis should fall between the ranges of -1 and +1. If you have a small amount of data, you may struggle with either of these two methods. In this case, you should run a Shapiro-Wilk test and a Kolmogorov-Smirnov test. Both of these tests can be run using statistical software. Discussing the intricacies of the differences between these two tests is beyond the scope of this course. What you need to know is that you are running these tests as tests of statistical analysis, where you are going to use a null hypothesis that the distribution of your data is normal and an alternate hypothesis that the distribution of your data is not normal. When you get the output from these two tests, you want to look at the p-values. If the p-value is less than 0.05, you reject the null hypothesis, just as we learned in hypothesis testing, and treat the data as not normally distributed. If the p-value is greater than 0.05, you should accept the null hypothesis and treat the data as normally distributed. If one test concludes normal and one concludes not normally distributed, proceed following the findings from the Shapiro-Wilk test. The second assumption of most parametric tests is that the level of measurement should be the interval or ratio level. In other words, the variable of interest should be at a continuous level of measurement. And this is quite simple to confirm simply by looking at what data was collected and how it was collected. And it should make sense for parametric tests that we need to have data at the continuous level of measurement. Parametric tests, by their design and definition, are working with the mean as the measure of central tendency. If you recall from one of our very first statistical lectures, data that are at the nominal or ordinal levels of measurement are categorical data, and therefore you would be unable to calculate a mean for that data. The third assumption common to many tests, parametric tests of statistical analysis, is independence of the data. Similar to the assumption of normal distribution, different tests will require different data to be independent. So what do we mean by independence of the data? Independence of the data means that no one data point influences another data point in the data set. This means that each observation of the data must be a separate and unrelated event so that one event cannot influence another. For example, if you are comparing groups to each other, every member should be in one and only one group. Independence of the data is generally achieved through random sampling. And as I said, these assumptions are not assumptions of every single parametric test. When we talk about dependent sample t-tests, we will talk about tests where we are looking at the same sample and comparing data either pre-test to post-test or comparing two interventions on the same sample. And therefore, since we have the same sample, there would not be independence. However, other tests, such as the independent sample t-test, will require independence of the data. So it is very important that you do not just memorize these assumptions, but rather understand the assumptions for each specific test, but understand the meaning of how to confirm the assumption. The fourth and final assumption that we are going to discuss in this lecture is the assumption of equality of variance. Similar to with normality and independence, the factor that needs to be assessed for equality of variance is going to depend on what variable you are using based on what test you chose. Equality of variance means that equality across groups should be similar. For example, if you are measuring blood pressure in group A and group B, the variance across the individual blood pressures obtained from participants in group A should be similar to the variance of the independent blood pressures obtained from participants in group B. To confirm equality of variance, you should use your statistical software to run a Levene's test, similar to how we did for tests of normality. Only this time, our null hypothesis would be that the variances are equal, and the alternate hypothesis would be that our variances are not equal. Again, we want to look at the p-value that we obtain from our test statistic from the Levene's test. If the p-value is greater than 0.05, we accept the null hypothesis and treat the variances as equal. If the p-value is less than 0.05, we reject the null hypothesis and treat the variances as not equal. Sometimes serious violations of parametric tests occur, and these violations would negatively impact the validity of the study findings if statistical analysis was run using the chosen parametric test. In these situations, investigators should use a non-parametric test, as these tests serve the same purposes as their parametric counterparts, but allow for a more conservative approach when the assumptions of parametric analysis are violated. We will now transition to a brief discussion of the assumptions of non-parametric tests. While non-parametric tests do not assume the data are normally distributed, they do generally have 3 assumptions that should be met in most cases. Again, every specific non-parametric test will have its own set of assumptions that must be met. There are 3 assumptions common to most non-parametric tests. The first assumption is that random sampling was used. The second assumption is a similar assumption to non-parametric tests in that the 2 groups that you are comparing are independent of each other. And the third assumption of non-parametric tests is that the level of measurement is at least ordinal. And this is because while parametric tests are comparing means, which requires us to have continuous data, non-parametric tests are comparing either medians or ranking the data, as in ranking it from smallest to largest, least to most. And we are able to determine rankings with ordinal level data. So it is undeniable that non-parametric tests have a very appealing property and that they require fewer assumptions, and the assumptions that they require are a lot easier to verify than the parametric tests. However, there are a few serious drawbacks that should keep us from always choosing non-parametric tests. First, non-parametric tests are generally less powerful than their corresponding parametric test when the data are approximately normally distributed. This means that there is a lower probability that a non-parametric test would tell us that 2 variables are associated with each other when they are in fact truly associated. Worded another way, using a non-parametric test when the assumptions of a parametric test are met increase the risk of a type 2 error, which you should recall is a false negative. Second, the results of non-parametric tests are less precise than the results of parametric tests because non-parametric tests describe the relationship between the ranks of the data or the medians rather than the relationship between the means. Furthermore, if the non-parametric test is relying on rank, an additional drawback is that some information about the data set itself is lost, because instead of looking at actual numeric values, the non-parametric test is looking at the ordering of the data values. So in summary, a good rule of thumb is to begin with the intent of using a parametric test. Check the assumptions and confirm if you can actually use the parametric test you desire to use. If the assumptions are violated, then proceed with checking assumptions and using the appropriate non-parametric test. This way, you always can ensure your results will be as valid as possible, both internally and externally. As a researcher or an investigator, you're going to put a lot of work into data collection. And the last thing you want to do is limit your analysis by not using the right test of statistical analysis. In the upcoming lectures, we are going to look at how you know which test is the statistical test you should use based on your data and based on your hypotheses.